Welcome back. This is Module 7 of Geography 385. Those of you that are keeping track, remember that we spent several weeks talking about the vector model, and that's a model which is a simplification and generalization that involves making the real world into sets of points, lines, and polygons. Well, it's time to talk about another GIS model in common use, and that's the raster model. I talked about some of this stuff back in Module 1, so a lot of this video will be review. Imagine the real world as that graphic that's pictured here in the upper left. We have streams, lakes, forests, terrain. In the vector model, we can represent things as lines or polygons or even points. In the raster world, what we're going to do is represent reality as a grid of equally spaced cells, and each one of those cells will have some numeric value associated with it that you can then link back to an attribute that will tell you what that value represents. Okay, so this raster model is a model that simplifies and generalizes into a grid or array structure composed of regularly spaced square cells. Now you'd like to have square cells, but they don't have to be square. They have to be regularly spaced, but you can have rectangular cells. Here's kind of an example where on the left what you have is an image of reality, and it turns out that an image is actually a raster model of reality. But this graphic indicates that we're modeling reality with a grid of cells, and in this case the red cells represent the roads and the blue cells represent the water. The roads might have a certain number associated with them so that you would have an attribute table that said this is a road and this is water. Alright, the raster model is going to be best for continuous geographic features, things that vary continuously across the landscape. The vector model generally is going to be better for things that have distinct features, that have boundaries between adjacent things. So in the vector model, we're thinking most of the time of the built world or the natural world that has distinct boundaries. With the raster model, we're thinking generally about the natural world and continuous phenomena like maybe elevation, temperature, precipitation. You can model using the raster or the vector model both natural and human-made phenomena, but generally raster is going to be better for natural phenomena. Okay, so remember the raster data model is going to have a grid. Here's the grid, regularly spaced cells. In this case, the cell size A and B is equal, so these are square cells, but they don't have to be square cells. And the reason I keep saying that they don't have to be square cells, if you go back to Module 2 when we talked about georeferencing, and you remember how latitude and longitude lines work. And longitude lines converge, so at the North Pole there's no distance between longitude lines, whereas at the equator there's maximum distance between longitude lines. So if you get raster data that's in geographic coordinates that hasn't been projected, you're going to have cells that won't be square, they'll be rectangular, and that becomes an issue with raster data processing. So in general, again, if you're going to do analysis with raster data, you may need to make sure that your raster data has been projected. Okay, this is a grid. The grid doesn't have to be square. You can have columns and rows of different numbers, so you can have differently shaped grids. How do you locate things in the raster model? Remember in the vector model we had coordinates of points, and lines were connected points, and polygons were lines that closed in on themselves, but they were all based upon coordinates, x, y, and maybe z coordinates. In the raster model you have coordinates for the corner of your grid, and then since you know the cell size, you're able to specify the location of another cell by how many cells over or up the cell that you're interested in is. So you have an origin, you have a cell size, and you have an offset. Here's an example of that. We have in this case a raster with the origin at the upper left corner, and this is the way most raster data will be. The origin will be at the upper left corner. And we know the cell size is 30 meters. How do we figure out where this cell is at? Well, we can count the number of cells. There's 5 cells over, and there's 5 cells down each cell is 30 meters, so we know that if we go over 5 times 30 equals 150, we go down 5 times 30 equals 150, we'll get to that point right there, which is the corner of that cell. So basically what we do is we add 150 to the x-coordinate, because we're going in the positive x direction. We subtract 150 from the y-coordinate, because we're going in the negative y direction, and we get the coordinates of the corner of that cell. And we can also reference things to the center of the cell, and in that case we're going to be going half cells, and you can see obviously how that would work. Okay, each cell gets a single value, and sometimes a cell doesn't have any data, and in that case you're going to have something called no data. So raster has this concept called no data, which is a certain value that's assigned to a cell that you don't have data for. And generally the definition of the raster data set will pick some number which is used for no data, and then when the computer sees that number it represents that as no data. So in a lot of cases it might be something like minus 99999 is no data. So when the processing goes along and it sees a cell that has minus 99999, it says there's nothing in there, I'm not going to process this cell. You can have cell values that are integers, and integers are going to be good for the categorical data. Remember, categorical is nominal and ordinal. You can have floating point data, and that's good for continuous data. So you can imagine temperature in degrees Fahrenheit might be interval data. Temperature in degrees Rankine, which is an absolute scale, might be ratio data. But you can have floating point or integer values for these cells. One of the issues with raster data is, since each cell is assigned a single or no data value, that value has to apply throughout the cell. So here we have a model, vector model with polygons, and the value inside of this polygon is 1 and the value inside of this polygon is 2. But we have a cell here that crosses that boundary between 1 and 2. So what value does that cell have? It can only have one value. So in this case the cell takes on the value of 2, and generally that might happen when more of the area is occupied by what would be 2 in the vector world than what would be 1. Sometimes you can average the two together, so maybe the value that would be put in here would be 1.5. But if you're looking at categorical data, let's say this is forest cover 1 and forest cover 2, if you do an average, 1.5, you don't know what kind of forest cover that is. So if predominant forest cover inside that cell is forest cover 2, then you would want to use 2. So there are rules that you can use when you're converting from vector to raster and raster to vector. You can also see where raster doesn't work as well as vector when you have distinct boundaries between features. Okay, this is a chart that compares the raster and the vector model along a lot of dimensions. I'll quickly walk through some of these. The raster data structure is simple, right? It's a grid. The vector data structure is complex because you've got points, lines, and polygons anywhere in space, and you have these rules about connectedness and closure and things like that. Storage requirements. For raster, if you're storing a value for every cell in your grid, you're going to store a lot of values. For vector, you can store a value for one polygon, for one line, and so you can save a lot of storage space if you can do it in the vector world. Coordinate conversion can be slow because you have a lot of data. It's pretty easy in vector because you're just plugging into an equation. Raster analysis can be easy for continuous data, and it can be difficult for network data. So vector is generally going to have easier analysis for network data than raster. You can do network analysis with raster, but it's more difficult. The precision of a raster data set depends on how big your cell is. Since the entire cell gets one value, then any location inside that cell might be the location of that value. So that's the precision of the position. In the vector, it's just limited by how good your coordinates are. Accessibility, it's easy to write programs, relatively easy to write programs in raster. In the vector world, it's more complicated because you have to deal with those geometries, which are more difficult to get at. Display, raster is good for images, but when you have discrete features, you're going to get stair-stepping or pixelation in your raster model. And so remember that continuous features are better represented using raster, discrete features better represented using vector. Okay, most of that stuff was review. Next time I'll get in a little deeper to the raster model and we'll learn a little bit more about how it works. And then we'll progress into raster analysis, just like we did with the vector model. We progressed into vector analysis. So that's what will be happening next time.